Hi, I'm Stevie C and the place to be. This video is part 2 of making multicolour LED fairy lights, this time using an alternative way of powering them from the mains. Just like last time, I'm going to show you a sped up video of me removing the blown tungsten lamps from my old set of fairy lights, marking the lamp holders for polarity, installing the new LEDs into the lamp holders and then reassembling the light set. So once again, that's the light set reassembled. So now we've got to put together a power supply to drive these from the mains. So this is the circuit I used last time. It uses a full wave bridge rectifier, which is basically 4 diodes arranged like this, and 4 2.2k resistors on each of the legs of the bridge rectifier. Now the main problem with resistors is that they dissipate energy as heat. So the circuit I'm going to use this time will use a capacitor to limit the current, and the capacitor will run cold. So here we have the new circuit we're going to use. We have the main limiting capacitor. This is what's going to be responsible for limiting the current. We have a discharge resistor so that when mains is removed from the unit, it discharges that capacitor. We have the same 4 diodes forming a full wave bridge rectifier. We have an electrolytic capacitor to reduce ripple, and then we'll have our 60 LEDs on the output. Now if we look at this diagram here, this diagram shows the AC waveform coming in off the mains. This enters the circuit here, and on each half of the sine wave charges up this capacitor, which allows some current to flow through the full wave bridge rectifier. The full wave bridge rectifier here converts the sine wave into that. So it's basically taking the negative part of the sine wave and flipping it, so that makes a positive DC. It's then fed into this electrolytic, which then smooths out the power, so you get a smooth DC signal with, in theory, no ripple. So when alternating current is applied to this capacitor in here, what initially happens on this part of the sine wave is that that plate charges up positive, and obviously that plate charges up negative. And then on this part of the sine wave, when it reverses, that plate becomes negative and that plate becomes positive. And this sort of oscillating back and forth is what allows a small amount of current to trickle back and forth through the rectifier to then be converted into DC and then into the rest of the circuit. So I've had a wee think about the values of components I'm going to use, and I think what I'm going to do is I'm going to use a 228 nanofarad capacitor to drop the current. I'm going to use a 1 mega ohm discharge resistor across that. I'm going to use 1N4007 diodes, they're pretty standard, and I'm going to use, I think, a 4.7 microfarad smoothing capacitor on the output. And obviously, the bigger the dropper capacitor in here, the more current is allowed to flow throughout the rest of the circuit. Now I'll show you why I've chosen the arbitrary value 220 nanofarads as a dropper capacitor. Well, what I'm going to do is I'm going to work out the total forward voltage of all LEDs like we did in the previous project. So here's all the LEDs I'm using and their respective forward voltages. So now I'm going to work out the total forward voltage for the entire light set. So all I'm going to do, like last time, is just add up all the numbers. So now I know my string is going to drop 148 volts. Because I'm using an electrolytic capacitor, this is going to be charged up to the peak mains voltage of 330 volts, in my case in the UK. So I'm not using the RMS voltage like we saw with the resistive dropper, I'm using the peak voltage. So if we start with the peak voltage of the mains and we take away the forward voltage of my light string, we're left with 182 volts that we're going to plug into the calculation to work out the size of dropper capacitor. I keep a handy cheat sheet of capacitor values and their equivalent resistances. I've just worked these out beforehand, but I'm going to show you how to work these out for yourself. And as you can see, 220 nanofarads, where is it? Approximate equivalent resistance of 14,468 ohms. So if we take that number, and again using Ohm's law, we divide that into 14,468, we get about 12.5 milliamps that the set of lights would run at. So that's well within the operating characteristics of the LEDs, so no 220 nanofarad would be perfectly acceptable. So in order to work out the equivalent resistance of a capacitor, we use this formula. 1 divided by 2 pi fc. 1 and 2 are just the numbers 1 and 2. Pi is just your usual 3.14159265358, yada yada yada. F is the mains frequency, 50 in this case, that's what the 50 hertz or 50 cycles per second refers to. And C is the value of the capacitor in farads. So we have to convert the nanofarads to farads. So I'm going to go ahead and plug the numbers into the calculator. And there we have it, 14,468 ohms approximately. So it turns out you can buy one of these little capacitive droppers ready to go on eBay. I say ready to go. I'm going to replace a lot of the components in here because I don't trust them. So if we take a look inside, there we've got our main dropper capacitor. We've got an electrolytic capacitor. That's only rated 250 volts, so I'm going to replace that for one that's rated to at least the peak mains voltage. So I'm going to replace that capacitor, the discharge resistor, and the electrolytic. So now that's the components replaced in the power supply, it's time to solder in the mains input cable and the LED cables. I've robbed this plug and cable off something else, I can't remember what it was. That's obviously going to go into the mains AC side. For grabbing the Fairylights. Got my input to them as well, so let's go do that. So that's us all ready for a test. And as usual, I don't know if this is going to work. Hopefully it will. It might go bang. Hopefully not, but let's find out. Bring the mains up. What voltage are we on tonight? 243 volts again. Ready? Cool. Yay! It'll work. So this set's running about 1.2 watts, as you can see in there. If we're going to 10 milliamps thereabouts. Meter's not obviously not accurate down to the milliamp, but I've just noticed this again. Why do I always seem to do this? Right, I'm going to go ahead and change this LED. There we go. So as I mentioned before, this capacitor in here, which coincides with this on the diagram here, this is what's responsible for limiting the current to the circuit. So if I wanted to drive these LEDs at higher intensity, I'd just have to swap out this capacitor here for a higher value. So it's got the 220 nanofarad in there at the moment. So I thought I'd maybe try a 470 nanofarad. So now we have the 470 nanofarad capacitor in the circuit. We've got the voltage to be dropped across the capacitor. Now 470 nanofarad is equivalent to 6,773 ohms. So if we divide that, the LED should run about 26, 27 milliamps. So we'll put that to the test now. There we go. The brightness is increased and obviously the power draw is increased. 2.6 watts now, but I really like that brightness. So there we have it. My second set of tungsten Fairylights converted to rainbow multicoloured LED Fairylights. I am really impressed with the results, even though getting the tungsten lamps out of the holders was a bit of a pain, but again I got there in the end. So all that remains to be said is like, subscribe, look forward to the next video, and I'll see you next time. Thanks for watching.